My name is Jonathan Hu, and I'll be talking about linear solvers inside of Trilinos. Yeah. Okay, so I guess I don't need to, I can probably rush through these. I didn't know what was coming ahead of me. So I don't think I need to tell anybody about Trilinos or, any of the capabilities or the architectures. I will mention, though, that it's used in a lot of internal applications at Sandia, as well as Office of Science applications and also user-led applications. And as mentioned, obviously Trilinos depends on Cocos and Cocos kernels, the capabilities there for on-node performance. And I just wanted to highlight here that there's a lot of linear solver capabilities in here inside of Trilinos. And the colors here are not particularly sort of significant for this talk. I will be talking about a number of these packages in here. And I do want to, before I dive into the packages themselves, I do want to mention there are a lot of Trilinos developers, and this is actually not a full list. I've almost certainly left people off of here, so I should have said this is a partial list. We have a lot of folks at universities who contribute, who are very active, and are working on their own applications and contribute back to Trilinos. We have a lot of people also at Sandia and then at other labs. So anyway, so this is it's a big effort. All right, so I do want to just jump into a tour of the packages, the solver packages inside of Trilinos, I do want to mention first, Kurt already said this, but the ePetra solvers are no more with Trilinos 17. So in particular, Amasos, Aztec 00, IFPAC, and ML, and that is multi-level, not machine learning. ML are no longer part of Trilinos as of 17. If you wanted those, you have to get, I think, 16.2 or something, one of those versions.
But you don't want those.
Well, I mean, actually, some people really like them, and that's fine. But I wanted, but there are replacements for all of those, and there are better replacements. Those are actually better. And the first one is a Krylov solvers library. It's called Belos. The lead developer here is Heidi. And so this is often when people are looking for solvers, linear solvers, the first thing that they want is a Krylov solver. And this is what is one of the capabilities delivered in Belos. So along with the other solver packages, Belos is C++. You can get the classic Krylov methods, GMRes, CG, BiCG, BiCG-stab, etc. Belos has a really nice capability in the sense that you can solve just standard sort of linear systems, AX equals B, single right-hand side, but it does support multivectors. And then you can also sequentially solve systems with multiple right-hand sides. And then you can also handle block systems as well. And it has some advanced methods, the block methods, seed solvers, it has recycling capabilities, and then it has a lot of other capabilities as well, like restarting techniques, different orthogonalization techniques. So anyway, this often forms the base of the linear solver stack inside of Trilinos. Now, the second thing that you're going to look for when you're solving a linear system, besides the Krylov method, is you probably want a preconditioner for it. And the first types of preconditioners that people usually start with are Jacobi or some sort of SOR type method, and those are provided through this package called IFPAC2. So you can get the classic ones, Gauss-Seidel, SOR, Jacobi. There's also polynomial preconditioners, different varieties of Chebyshev polynomials. If you wanted to move on and you wanted to do something heavier duty, like an incomplete factorization, you can get that as well. There are CPU-based factorizations, both traditional like ILUK or ILUT. There's also iterative factorizations in there. And then IFPAC2 also has interfaces to incomplete factorizations that are available in Cocos kernels. So if you're running on a GPU and you wanted to invoke those, you could use those as well. Now, if you wanted to move on and you wanted to do some sort of domain decomposition, IFPAC2 also has the capability to do additive Schwartz, both with overlap and non-overlapping. And you can, within a subdomain, you can apply various subdomain solves. So you can do direct solves, incomplete factorizations. You could use one of the other capabilities above if you liked. And then there's some block methods as well. And IFPAC2 can be used standalone. Like if that's sufficient, you can do that. You could use it as a preconditioner to the Krylov method, or you can actually use it inside of a multigrid algorithm if you like. All right, so speaking of multigrid, this is if you wanted to move past sort of the standard techniques inside of IFPAC2, then you could move on to multigrid. And this is provided by this package called Mulu. And multigrid, this is just a sort of a cartoon. The idea is that you want to solve some linear system AU equals F. And you can do this by essentially solving a residual equation on some coarse system. And you approximate the error. If you actually knew the error, then you could solve the residual equation exactly, and then you'd have your solution on the fine grid system. But what you do is you project the residual equation down, you solve it there approximately, and then you can do this recursively, and then you push the solution to that residual equation back up, and then you have an approximation to your error on the fine grid system, and you can do a correction there. And so there's sort of a few different parts to multigrid. There's forming the coarse grid systems, and then on each level, there are very simple solvers that we call smoothers. So Mulu depends on a lot of the other capabilities inside of Trilinos. So for the smoothers, these simple solvers, it uses capabilities from, it can use Jacobi, Gauss-Seidel, polynomial smoothers. You can use much heavier weight smoothers as well. Developing these grid transfers, these transfers between the different levels, that's a research topic unto itself. There are unstructured algorithms for doing this. The main one inside of Mulu is something called classic smooth aggregation, which is a little bit different than what Hyper provides. It's a different branch, if you will. But that's used to great effect inside of Sandia and outside as well. There's a capability, an AMG capability for tackling non-symmetric systems called Petrov-Galerkin. And then there are some specialized multigrid methods. So in particular, there's one for particular forms of Maxwell's equations. So Christian Glusa will be talking about this a little bit later, actually tomorrow. And so as Roger alluded to, a lot of the capabilities inside of Trilinos, they sort of are predicated on having unstructured meshes. But we do have algorithms for structured meshes or semi-structured meshes. And so there's some semi-coarsening capabilities, semi-coarsening AMG. And there's also a structured grid aggregation-based multigrid. And as I said, Mulu would basically be a car without an engine if it didn't have the rest of Trilinos. So it depends on T-Petra, that's a must. And then for the shared parallelism, of course, it relies on Cocos and Cocos kernels. And then for the smoothers, it gets it from IFPAC2. It can use Cocos kernel smoothers. For direct solves on the coarse grid, it uses Amisos 2. And then there's this load balancing using Zoltan-2 that Roger talked about. And that's a pretty important piece as you start to scale out or increase the size of your problem and increase the scale out onto supercomputers, being able to both load balance data and move data to subsets of MPI ranks. All right. Okay, so another linear solver package inside of Trilinos is a shared memory direct solver and incomplete factorization package. It's called Shilu, and there are basically three main pieces. The first piece is something called Basker, and it's a threaded direct, sparse direct solver, and it specifically targets non-symmetric systems. And it is a variant of an algorithm called KLU that was developed by Tim Davis and his colleague back in 2010. And I think KLU is, I think the K, somebody asked, in a previous presentation, what's the K? I think it stands for Kent, like Clark Kent, because it's an alternative to SuperLU. So that's a little fun fact. The second main piece in Shilu is something called Taco, which provides sparse symmetric factorizations, so like Cholesky, LDLT, symmetric LU, and it is GPU enabled. And then the third main piece is an iterative variant of ILUK and sparse triangular solves called fast ILU, and it's very similar to a technique developed by Edmund Chow back in 2015. All right. The next linear solve that I want to talk about is something called Frosh, and this is an overlapping Schwartz framework its actual main developers are, well, you can actually see here there are Sandia developers, but there are a lot of developers over in Europe at a number of different institutes. And the idea here, as I mentioned, it's overlapping additive Schwartz. It depends on T-Petra. Obviously, it's written in C++. It can run on CPUs and GPUs. And you can access it through Stratumicos. And you can think of it as a two-level method. So you're doing sort of classic additive Schwartz on the fine level, and then does an algebraic construction of the coarse level using extension methods. All right, and here's an example provided by Alexander Heinlein, one of the main developers of Frosh, sort of demonstrating the scalability. This is just for a heterogeneous 3D Poisson problem. There are about 8 orders of magnitude in variation in the coefficient here. So it's a very high contrast problem. And across the bottom, you have the number of subdomains. You have the total time on the top, and they are comparing here parallel efficiency, and they are comparing to GDSW, a couple variants of GDSW. And so they're getting some pretty nice scalability here compared to the other two. Right. And then, so I want to mention the next linear solver, which is something called TICO, and it's a monolithic block multiphysics preconditioner, and it provides sort of block inverse schemes. And so the notion here is that you have some multiphysics system, and maybe representing different physics, and you want to invert those different blocks. And TICO provides a capability of sort of doing like a block Jacobi or a block Gauss-Seidel or other block type method, where you can actually then decide, well, how do I want to invert these blocks? And you can invert those blocks using some other solver within Trilinos. and it can be applied to PD systems, for example, Navier-Stokes. It can also be applied to other multiphysics systems. In fact, Malachi will be talking tomorrow about it, I think applied to a variety of other systems. The one very nice feature is that you can actually start with something in .CRS form and then actually tear it apart and reassemble it into large block systems. Let's see. And yeah, I think that's all I want to say here. All right, so if you want to get started with the linear solvers, there's a few different resources for new users. How many people are actually new users of Trilinos here? Are there any new users? Okay, there's a few. All right. So there are different levels of sort of, I guess, tutorials here. So there's a set of tutorials that are typically given at the ATPESC workshop, which is held at Argonne every summer. And those are updated each year. Christian and a few other folks typically go and give these lectures. I think they're also recorded as well, so somebody could go and look at those. And those are, I believe those are actually interactive, so you can actually, or during the workshop they're interactive. I don't know if they're interactive at the moment. We also have a tutorial specifically for Mulu. And it's there on github.io, and we are planning to distribute it as a container that is not quite ready yet. And then there's also a few user guides that you can go and look at. So if you actually wanted to test some of the solvers, but you didn't want to commit to Trilinos, we do have the possibility, we have a standalone driver that you can sort of kick the tires and decide if, well, are the solvers here, are these something that I want to pursue more? And the driver that I want to point out is one that is available through Mulu, and we use it actually a lot in our development cycles, but we often, when people ask questions, we point them to the driver and say, well, here's a canonical example, and you can try things out here. So it depends on gallery that Roger talked about. So you can, if you don't have a matrix, you can generate matrices. You can specify the type of matrix you want. You can specify the size. There's Poisson, convection diffusion, elasticity. If you do have a matrix, we can read that in, and it will distribute it in a parallel fashion for you, so you can read it in on a single process. You can read in, we typically...
In case you needed to know.
Okay, nice. So, let's see, where was I? All right, if you have a matrix on the right-hand side, you can read that in. And then you can test a variety of solver and preconditioner combinations. So Krylov methods. This is an input deck which was readable on my screen. It's not readable here, but it's for multigrid. But with that same deck, you can also say, oh, I actually don't want to do multigrid. I just want to test like the SOR methods in IFPAC2. You can do that. Or, oh, I just want to actually use a direct solver. You can do that. Anyway, so the input deck actually lets you try a lot of different things, not just multigrid. And so that's a really nice way to sort of dip your toe in the water and without sort of fully committing. All right, and I think actually, and this is just sort of obligatory scaling plot. It's a little bit old at this point, but this was actually generated using the driver on the previous page, and it was run on Frontier. And so it's a very simple thing to sort of take this driver and just run it out to, in this case, 2,000 nodes, right? Very easy to do. and sort of, test out, kick the tires, and sort of, yeah. Anyway, so let's see. All right. I did want to mention there's some related talks. I mean, obviously you guys probably know this from looking ahead. I will be talking about some recent developments in linear solvers. Malachi will be talking more about TICO. Christian will be talking about Maxwell's equations, multigrid solvers for Maxwell's equations. There's also a few application talks as well that use solvers, but and those are on Thursday as well. Anyway, we've got some time, so I'm happy to take questions. Yep.
So several of these solvers have stuff that are able to go on the GPU. Is there any kind of general advice that you would give for which things would give the easiest wins if you're trying to say, hey, I'm using Trilinos on the GPU, and how much of a performance might you expect?
I mean, what kind of problem are you solving?
Use precondition GMRes for diffusion solves with heterogeneous coefficients.
I mean, well, you would use multigrid, right? That's you would use Baylos precondition by multigrid.
Yeah. That's what we're already doing on the CPU anyway. But
right.
But
yeah.
are there any options that I should change to say, am I gonna just instantly switch this over? Should I see X% speed up? Is there something I should expect or something I should be worried with? Yep.
I will just mention for the heterogeneous coefficient, we actually have an LDR project that we're working on to incorporate that to help inform algebraic multigrid to take advantage of that. So if you're interested, Chris Siebert is probably the best point of contact.
And actually, Chris gave me a slide that I'm going to show tomorrow with some results from. Actually, Christian gave it to me, but
Yeah, we just converted
yeah.
from U factor to T factor, so something GPU stuff is available.
Yeah.
So I want to know what I should try first.
Sure. I mean, so I will say that in multigrid, the classic thing to do is you would use Gauss-Seidel. That's what people do, but that's going to be pretty poor on a GPU, and so we typically we'll use Chebyshev of some kind there, right? Because its kernel is a sparse matrix vector multiply. And then I guess the other thing is you maybe wouldn't do a direct solve. That may actually just be. It's not that it wouldn't work. It's just unnecessary on a GPU.
Yeah. We had been using Super LU for a while, and even on the CPU, that doesn't really scale that well anyway. So.
Right. So. Yep.
Well, thanks.
Yep.
Alrighty.
Okay. Does your phone have anything else to say?
No. You can ask it later. But okay, unless there's other questions, we can break a little early for the coffee break. We'll be back here. I think it's at 3:50. Alrighty, thanks.
Thanks.